Thank you very much. Thank you very much for the kind introduction. And my apologies, I can't be there in person. I was joining last year. It was great fun, so I'm very jealous of everyone who gets to enjoy the blockchain salon in person this year. Yeah, so my talk has a pretty long title. So building decentralized applications for smartphones, energy measurements for practical protocol design. But literally, it boils down to this part. So if you're interested in any of these words, hopefully you find the talk interesting. It's more on the practical side, but I think still very relevant to talk about and might be interesting, especially for those of you who are implementing such protocols, especially with mobile users. So my general point is that we too often assume stationary computers when we talk about all kinds of decentralized protocols and applications. We have this infamous plug in the wall that provides us with unlimited energy, and we have reliable and fast connectivity. And usually the giveaway is somewhere in the papers, in the evaluation section, where everything is tested just using some AWS EC2 instances. However, smartphones really have become our primary computing devices. Most people who go online now around the world only have a smartphone, and they never go through having a computer as their main device. And we have two important challenges when we talk about smartphones. One is that we have the limited energy supply, and the other one is that we have to work with sporadic connectivity. And for today, we're going to focus on the energy supply. And I really believe that we can only optimize and improve things that we measure. So this talk is also going to be about measuring energy consumption. So what we really want is we want to measure a ground truth. We don't want to have any proxies because those modern smartphones are big black boxes. It's really hard to predict what's happening on the hardware layer, what the actual energy consumption is. And ideally, what we do is also easy to use by others. So others can replicate our research and do their own. And we're interested in both measuring average power, for instance, of protocol runs in the background, and individual operations that we want to optimize. And of course, when we measure, we're interested in high fidelity. So we want to be precise in what we do so we can actually optimize with confidence. And throughout the talk, I hope you take 4 things away. One is standard cryptography is cheap, so you don't need to worry about that at all. If we come to zero knowledge proofs, they can be really expensive. And communication is a big part of energy consumption as well. And their radio transmission patterns matter, so we have to think about those carefully. And cover traffic, as we would usually use them in mixed networks, can be really costly. And throughout the talk, I will assume we have kind of a battery of 8,000 milliwatt hours. But I will not talk about millijoules and milliwatts because I reckon for most in the audience, those metrics are quite unintuitive. So instead, we talk about percentage points. And you can imagine if we start with a fully charged battery and then after 12 hours, we are left with 40%, then, well, over those 12 hours, we lost 60 percentage points or 5 percentage points per hour. Cool. So how do we actually measure things? So what we did is we tried to build the simplest thing that works. And what we have is basically a few 3D printed components that any 3D printer can create. So we have like a holder for a battery and an inlet you put instead of the battery into the smartphone. They're connected and also connected through a power sensor. And that power sensor then talks to an Arduino. It's just all sticked into a breadcrumb board, so you don't even need to solder. And that locks the data to the computer. So we can measure around 2,000 samples per second at 1% accuracy. So that's actually quite decent for such a low effort project. And with that, what we can easily do is measure long protocol runs, because all we do is we start the protocol, then hit record on the computer, hit stop on the computer, and then look what the average power consumption is over that time period. However, what we're also really interested in is measuring individual operations. So if you think about optimizing, for instance, your cryptographic routines, or want to know why is the protocol using a lot of energy and how it is spent, then we want to do that. And with the setup that I just described, that's a bit difficult. So we just do one trick beforehand, and that is we synchronize the clocks. So that means we have a little USB device that we also connect to the digital input of the Arduino. And we run that at some point before our experiments to synchronize the clock. And afterwards, when we run our experiments, we just make sure the Android phone also logs timestamps as it executes our tests. And then we can later overlay that over the data that we measure at the computer. So that's all the hardware for now. Let's look at some results. So this might be something that now starts to interest a few of you. So this is the standard Android function for generating a relatively large RSA key. And what you can see is, well, it takes quite long, a bit over 3 seconds. And once the frequency of the core ramped up, we are at around 5 percentage points per hour. That is not terribly much. And so this looks quite decent. But most interestingly, when we compare that to more modern key schemes, for instance, elliptic curves, then those are, of course, way faster because we don't have to look around for a long time and search prime numbers that we're happy with. We can just start with the seed and then generate or curve parameters from that. And general, these are the most expensive operations in standard cryptography that you can do on the smartphone. And even the most expensive ones, which is generating RSA keys of a large size, you can do a few thousand times with a battery charge. And there's definitely nothing to worry about any elliptic curve operations or just using RSA keys. Those operations are all really cheap. So we can tick that off and take that home with us, that we don't need to worry about those standard cryptographic operations. What, however, is more interesting are ZK snarks, because they have become a very popular building block for privacy-focused protocols, because they allow us to prove a statement without revealing private input and without, well, giving any knowledge to the verifier. And our smartphone could be a prover trying to prove to the network and its peers that it has truthfully done something, and or as a verifier. So some other part of the network tries to verify us that something was done correctly without revealing to us what the underlying secret inputs were. And in practice, when we talk about proofs, they're usually relatively large. So for this talk, I looked up the Zcash repository, especially the rank 1 constraint system circuits for SafeLink and Sprout, and they sit around 100,000 constraints up to 2 million constraints. So they're actually quite large. And we use them in our experiments. We're kind of capped at 500,000 because after that, we run out of memory with the implementation we use. But that is definitely something that where we can optimize and hopefully also run on a test device at some point. So let's look how proving 500,000 constraints look like. So what we did is we took the ArcWorks Rust library, compiled that to run on Android phone, and we just used the most standard gross 16 configuration. And what you might immediately see, our y-axis goes way higher, and that is because the implementation uses multiple cores. And you can see probably towards the beginning, we're around 5 percentage points per hour. That's when we saturate one core really well. But then when we look around 20 to 30 seconds, that is when the beefy part of the calculation kicks in, and the Rust implementation can really use all cores. And then we start to use substantial energy. You might also notice this takes a long time overall, in addition to the high average power consumption. And it also brings home the point that if we just use proxy metrics just as runtime, then we might be off by a large amount, because the power consumption can vary a lot depending on your implementation. And naturally, if we look at something with less constraints than as expected, that all scales down quite well linearly, but even 100,000 constraints runs for 10 seconds at a high power rate, which is not ideal. But lucky for us, verifying is pretty cheap, because that mostly scales on the number of variables, and the witnesses that we see for practical proofs are relatively small, which is great. This is a bit of the summary table, and what you can see when we prove, then we are at around 0.2 percentage points for every proof operation of 500,000 constraints. And in practice, that means, well, we can run 500 with a battery charge. So we better don't do those too frequently throughout the day. But DK snarks are very interesting, also because of the sporadic connectivity. And that is because they're because of the non-interactive bit of snarks. So they work really well in the world of smartphones, where a smartphone might be offline during the day, comes online at some point, gets some updates, can verify them without having to interact. Just one download is fine. And it can also be smarter in that, for instance, delay the proof to later when it's on charge, and do such things in a bit more an asynchronous manner. So that was a quick detour into ZK snark. So there was some research where we're just starting, so I thought I'd include some sneak peek into the presentation. And the next bit is about radio transmissions, and that is motivated, or that motivates exactly why, for instance, all the non-interactive protocol bits are really interesting. And on mobile, the pattern of how we communicate matters a lot. And to understand that a bit better, let's look at a sample power trace. So what we do here is we send and receive roughly 100,000 bytes TCP over 4G. And this is what the power trace looks like. In the beginning, you have this one section where the modem wakes up, it talks to the cell phone tower, and makes sure it gets assigned the necessary resources to actually communicate. Then we have the active send and receive phase, where we send data and then receive data. And then we have something we call the tail latency. So because the underlying operating system doesn't know we're done, it keeps in kind of like this twilight state where it's very easy for it to send and receive more data, because, for instance, the server might send us more, or we might send another packet soon. So it wants to avoid going down to the lowest power state and then having to reconnect again. And this tail latency then also makes it clear why some communications patterns are more convenient than others. So for instance, if you imagine that you send a single byte every 5 seconds, that is way more expensive than sending a few every minute, because then we only need to go through that cycle once. What's a bit tricky is that tail latency is kind of a black box, so it varies between phones and networks, and that makes tweaking and evaluation hard in practice. Yeah, so that's a very brief summary of that part. And where it becomes relevant is when we, for instance, talk about copper traffic. With a lot of decentralized networks, what we want to have is we want to protect them against traffic analysis. We want to make sure we can communicate anonymously without anyone learning who talks to whom and when. And one big vulnerability that many anonymity networks have is traffic analysis. So, for instance, if you put yourself in the shoes of the global adversary and look at this diagram, you can spot, for instance, the traffic patterns of A sending 2 small packets followed by a large one, and then 2 small packets followed by a large one arriving at C. You don't have the ability to really follow along what happens in the anonymity network, and that anonymity network in this context could be anything from Tor to mixed networks to some PIR scheme. But still, we have these traffic patterns that are easy to spot and make it easy to confirm suspicions who might be talking to whom. So what we ideally want, we want to hide them. And if you been here last year, so might remember this slide, what we do is we use cover traffic. So instead of sending application payloads as they come, what we do is we have a fixed timer that sends an encrypted packet every 5 seconds. And if there's something ready in our payload queue, we send that. But if the payload queue is empty, we send cover messages instead. And of course, all those messages are encrypted and padded to the same size, so they don't leak any information. And what we can now do is we can test different parameters and sizes. And this is kind of a heat map comparing 4G and Wi-Fi. And what you might immediately see, the Wi-Fi one is way more green. And that is because Wi-Fi doesn't in general have this tail latency problem. It's way cheaper to also send at a higher rate. There's no like really bad optimization point. It scales relatively linear, whereas in 4G we quite quickly get into very expensive territory. And the interesting thing to observe here is because, by the way, we chose the intervals on the x-axis and the size on the y-axis, it's exactly the diagonals which have the same throughput. So all these configurations send the same amount of data per second, but with vastly different energy consumption. So this is a really easy way where we can optimize for mobile, making sure we don't just pick the highest frequency, which is nice on computers because it gives low latency, but we choose one that also optimizes for energy consumption. We actually did a bit more work on this, on feasibility of such anonymity networks with cover traffic. So we got a paper from last year that also looks at Tor and VPNs. And a student of ours, Jackie, has written his bachelor thesis on actually porting the NIM mixed network to Android and then also doing extensive measurements. So if you're into this kind of stuff, that might be interesting references for you to look at. But yeah, what we can take away is that cover traffic, especially if not carefully chosen, can be quite costly on mobile. So we have to be smart how we implement our vision of anonymous communication on those devices. This talk really provides a glance at the problem and at some of our measurements. There's much more to speak about, but in the interest of time, we're limited to 18 minutes, and especially the limitations of what I showed you. Like, it's only one Android device, it's only one network operator, relatively simple scenarios, and only part of the configuration space, especially with the knowledge proofs. You have a vast variety of configurations and implementations to choose from. So there's a lot more to be researched and looked at to find the optimal solution. And yeah, there's a lot of interesting work to be done. There are interesting areas in the trade-off space to look at. We can do way better with adaptable designs. We need to take hardware constraints into account. And if you work on anything where you think this is very relevant, well, let's measure together and potentially collaborate. And that brings me to the end. So don't hesitate to reach out, and you find all what I discussed, the hardware as open hardware schemes, and all the software and our measurements on our GitHub. Thank you very much.
Thank you. Other questions?
more just a comment. So benchmarking these snarks is kind of a nightmare, and especially because most of the people writing them don't really, they have a particular story they're trying to sell. It would be very funny if your kind of setup became sort of the gold standard for benchmarking some of these things.
Yeah, that's a very very valid point. I think at the moment, as we start with it, it's very overwhelming just to look at the entire space because there's so much also coming out every week. So I just thought I'd choose the most common, most straightforward representative example for this talk. But yes, that's absolutely true.
Hi, this is Sebastian Steinhaus from TUM. Great talk, thanks a lot. I have one question regarding the hardware setup. So you wired an actual battery, and doesn't this make the setup more complicated than maybe virtualizing this battery with a sophisticated power supply that can mimic the battery if you think of scaling in the future? So just for also reproducibility, because you might have some deterioration in the battery if you do 100 runs with your tests and these things, just for also getting then really good standardized values.
Yeah, that's true. So at the moment, because we measure both voltage and current, we actually get the power consumption that's drawn, even if the voltage and the battery drops. But I agree, it's like at the moment, you need to recharge the battery. That's a bit of a hassle. But where we thought this is probably the cheapest option for people who already have the phone, because you don't need to buy a lab-grade power supply. But yeah, that should be quite easy to just replace that battery with a proper power supply. Thank you.
Hi, David Guzman from TUM. Interesting work. Maybe a silly question. What does this communication pattern include? Is it an entire handshake for TCP, TLS? And the second question, what does this idle means? It's like AC case, or what do you really mean there?
Yeah, so first part of the question, so the figure that I showed you, that was taken from the one paper, and basically what we do is we mimic an implementation of the loopix network. So that has a persistent TCP channel to provider node, and then sends packets back and forth. And the idle that I showed in the radio communication graph, that is basically, I mean, at that moment, nothing is happening. Just the phone modem and the network operator think it's a good idea to stay in idle state, regardless of what's happening. So that even happens if you, for instance, send UDP packets and you don't have anything going on as a connection. It's just anticipating another connection and doesn't want to go through the full cost of reassigning resources in the communication channel.